Hey AP, this video is on deviations from the ideal gas law. So up until now, we have talked about gases as behaving ideally, but we also need to understand that in the real world, gases don't behave ideally. So we're going to talk about what attractions they have that we ignore with our kinetic molecular theory, and then we'll talk about the van der Waals equation, which does some correcting for that. Good news is we don't have to do calculations with this. However, we have to problem solve and do some explaining. So no math in a complicated equation, but we need to explain why the equation exists. So when we have deviations from the ideal gas law, they happen under high pressure and low temperatures, and they're going to break two parts of kinetic molecular theory. So first, when gas is pressurized, so my high pressure situation, and that's pressurized into a small space, that means that the size of the particles are going to play a bigger role. And we can see that here. If we figure this is like zoomed in. So if I have small particles, they can bounce around. They're going to have less collisions compared to my space gets smaller around my particles, or my gas is pressurized into that small space. My gas particles are going to occupy more space inside my overall volume. So the larger they are, the larger they are, the more space that they take up, the more collisions they're going to have with our walls of our container. Therefore, we're going to have a higher pressure than we originally calculated for. So if we pretend that gas molecules only look like this, we're going to get a much lower pressure than what's actually true. Furthermore, if we're at really low temperatures, that means that there's going to be less energy. The particles are moving slower. That means that when the particles start to slide past each other, they're going to actually get attracted to each other, whereas regular gas particles, our ideal gas particles, are moving so fast that their speed overcomes the attraction, so they just dart past each other. But when they slow down, they start to get attracted to each other. When they're attracted to each other, now that means that we're going to have less collisions. So four singular particles are going to have more collisions than when they get attracted to each other. Now there's just two particles moving around, so there's less collisions per second. So high pressures, which also mean that we are having molecules occupying more space. Low temperatures means they're moving slower, we're going to have more attraction. So those are our two situations that we're going to focus on here. So if we consider real gases, we can think that, well, particles actually take up space, even though we pretend up until this point that gas particles don't. But they actually do take up space, especially in small volumes and high pressure. We can see that the observed volume is artificially large, right? Artificially large. So we have to correct by subtracting a factor, and we'll see what that is in a minute. And then actual pressure is lower because molecules are attracted to each other, right? So really molecules are attracted to each other, so causing less collisions with the walls of the container. So we have to correct by adding a factor. So we add a factor to make up for collisions. We subtract a factor to make up for the fact that they actually do have a volume. So our gases behave non-ideally under low temperatures and high pressure. Particles with significant intermolecular forces, so they're significantly attracted to each other, and particles with really large sizes. Okay, so these conditions you're going to want to know as ways that make gases behave non-ideally. So we have this formula, and like I said, we're not going to do, I think we'll do one calculations to illustrate the point in our practice problems, but otherwise, we're just looking at the fact that here are factors that are affecting it. So we have our A factor and our B factor. So our A factor is here, it's getting added to it. This A factor is for particles with strong intermolecular forces, so it helps us with our attraction. Okay, because we said that if there's attraction, we need to add a factor because the actual pressure we find is lower because when the molecules are attracted to each other, there's less collisions. So we have to add a factor. And then we subtract our other factor, which has to do with when they take up more space than we think that they do. We have to subtract that they take up more space. And that is our B factor here. So we still have pivMERT, P times V equals nRT. But then we have our fudge factors here, which help us modify this equation to become more real for real gases. Here, and then N is moles, and then we have our V still for our volume here. So long story short of all of this that we need to understand is that deviations from the ideal gas law happen under high pressures and low temperatures. High pressures cause size to become more of an issue than we allow it to be. Low temperatures allow for attraction to be more an issue than we allow it to be. And then we'll explore this more in class tomorrow.